I already provided a link to the slides, so that was in the reminder for the meeting, and I will include it again when I will distribute the recording. So if you need those, you will get them. So PG, thank you for reaching out to present about this, and looking forward to your presentation.
Hey, thank you, Fred. I appreciate you distributing the slides, because I probably have to either talk very fast now or skip a bunch of slides, so we can. Now, I'm happy to stay. I don't have a dead stop at the end of the hour, so this is our hot topic, so I'm happy to stay.
Yeah, we can make we can give you a bit more time. There's no hard stop at noon, although some people may drop, but then there's the recording, so take your time.
Okay. Good, thank you. So this is my first exploration into Eclipse, so delighted to be here. It is, after talking to Fred, a bit of an exploration. The appropriateness of open sourcing the Causal digital twin through Eclipse is one of the things I'm trying to explore. And I suppose on your side, many of you are probably quite familiar with Causality, and then how does it come together in the case of IoT. A couple of years ago, Causality was, a slew of press reporting on it. Jediah Pearl's name comes up all the time. But it picked up a lot of momentum, and it turns out it's pretty hard stuff. And most of the applications were in social sciences and healthcare and so on. So early this year, I spent time for the last 6 months figuring out how to bring it into IoT for a couple of reasons. I'm a veteran of IoT applications from Rockwell Automation days, many years ago. So I've always felt that IoT of today is not really delivering the value for our business customers. And I have a view of why that is so. So Causality to me was a absolute what will break open that dam and will allow much more significant IoT applications. So a couple of things we quickly clarify. We all know this, correlation is not causation. The person in the truck, he's pushing and the truck is moving, it's correlated, but that's not causation, we know that. And the difficulty in causation is, as opposed to correlation on the top, correlation is not directional. We say X is correlated to Y, but that's not correct. X and Y are correlated. It's together. There is no directionality. But on the other hand, when it comes to causality, direction is super important. For example, direction going from dog to man, dog bites man is not news, but man bites dog is big news. So directionality is very important. All of what this means is causality and handling it in mathematically correct ways are significantly difficult. So for a working definition, this is in philosophy, this has been debated, very dicey definition, but thinking as an engineer, I'm comfortable with this operational definition. X causes Y means changing X alone will change Y. Something else changing may change Y, but we are only talking about X and Y. So that's a pretty good definition, and we can be pretty happy with that. And the reason why it's important in IoT case is, as any who have deployed this in real applications, we know that when there is in a condition monitoring situation, there is an alarm. It is not enough just to say, let's say the bearing is running hot or there's a lot of vibration. You can't keep on changing the bearing, because every time you'll be just changing the bearing. And that's not what happens on the plant floor. The technical experts will get together and try to find a root cause so that you don't have to keep changing the bearing. So this has been recognized, and there is a fairly recent article talking about this. And this, I believe, is the reason why IoT has not, in my opinion, really lived up to its promise. The first part It's happened. We all know about this. We got all kinds of predictive analytics and so on. But to move to the next stage, to prescribe what needs to be done to improve quality or productivity, because these are all things that impact the gross margin, we do not have a solution. And that is because of this kink in the growth curve. We have not uh, come to grips with causality and how to apply it. So now we know that where causality will apply in IoT is going to be but through automating root cause analysis. At least that's one way that we will do. So if you look at the history of it, using machinery monitoring, but that's a canonical use case. This could be for utilities or smart cities or any of them. So in condition monitoring in olden days, I've seen this personally, where the mechanic will put a stethoscope on the car and he's monitoring the condition. And now the picture in the bottom is actually the product I developed in Rockwell Automation, deployed in some paper plants or one of those plants. It records all this data and it can produce alarms, and you can go drill down and look at various things. As root cause, the way it is done is it's really experimentation. So when you see a problem, a few people or one expert will think about this and say, let's do this and see what happens. So that's how they get to the bottom of it. There is no new way of doing that. And that, I believe, is what causal digital twin will lead us to. So to drill that point down, this is from a recent conference. They were talking about the benefits of IoT. It's great. It's, we do all these things. We get the data channels, we visualize it, and so on. And in my opinion, these are the key benefits from condition monitoring, but not all of them are really realizable. These three, I agree: predictive maintenance, prevent damage. Those definitely, with our current state of IoT, condition monitoring delivers. But we need to go further if we want to do productivity improvements, analyze and optimize processes, and so on. So that is where typical deployment, if you think about it, there are sensors on multiple devices, let us say. I'll go back to manufacturing because that's where my solutions were deployed in paper plants and steel mills and factory floors and so on. So multiple machines will have multiple sensors. The reason why we have multiple sensors and multiple channels of data is that they may be interconnected. So if there is a series of machines, we want to monitor all of them, a collection of them. So this is not about just one machine and its asset performance management. We are taking it to a collection of machines. Then when you're collecting data from multiple channels, we need a different approach because our current methodologies do not address it. And I'll quickly talk about that. I'm going to, because of the time, I'm going to skip a bunch of slides. I'm assuming this group is well aware of how digital twin works. Just to give a software architecture kind of thing, where it fits in, you can see it is in one of my solutions on a platform. It's deployed here with edge interactions, as well as some work being done, Causality engine in the cloud. But this is probably more important. How does this causal digital twin service work? It's like most other ML type. The connectivity from the edge is there, and then you collect a whole bunch of data. So this is like a training, testing kind of regime. So you call the API, the Causality Engine API, to generate what is called a causal graph. This is a key piece of information. This actually tells you what are the potential causal connections between them. There are two ways to do it. If in the case of a bunch of machines connected together, a domain expert, a machine dynamicist, will probably be able to sketch out a pretty decent causal graph. But then I'll talk about a methodology called fence graph, where it is estimated from the data, so you don't have to know. But I'm always a believer in using both the human experts' intelligence as well as what we abstract from the data. So a combination gives us a pretty reasonable causal graph. Then there is an algorithm, so we have many. So I've developed a bunch that can update these causal link weights. So this is saying X is causing Y by that much amount, and X is not causing Z, and so on and so forth. Then the way in which it is used on a real-time basis or day-to-day basis is number 4 is really the current condition monitoring. It's just that this causal links, rather than just the vibration amplitude, would be a much more sensitive detector of faults and much better predictor of future state. It is simply in which there is more information abstracted to the link weights rather than just the vibration amplitudes. So one would expect better condition monitoring. But number 5 is what is unique about this. Is so-called what-if analysis, or in causality, we call it counterfactual experiments. So things, what if I had done, would that have happened? In causality, that is super important in addressing what kind of improvements is possible to improve performance, speed and quality, and reduce waste. So this is how it'll be utilized. So setting this up as a very large background, we all know what digital twin is. It's essentially, you had to collect data from the universe, and connectivity and data platform super important. And then you have to extract information, and closing the loop today is usually visualization. There is no automatic impacting a machine, at least in other than in tests and POCs, but eventually that'll happen. So if you think about it, these are enablers. This is where the middle row is where the main action happens, information extraction and closing the loop. And then we have to make sure it works. So my own way of, I don't want to throw in new terminology, I'm comfortable with digital twin, but I tend to sometimes call it digital nervous system, because we should not forget that this is like the peripheral nervous system, the top row that brings it in. The central nervous system is what's in the middle. All of them have to work together for a successful digital twin. So this is just a very general statement about digital twin. So let's get to what's happening with multi-channel data and IoT. So for now, let's stipulate that any worthwhile IoT deployment will have multiple channels of data simultaneously monitored. There'll be some that won't. In general, it's the case. So let us say we are looking at, so let's say these are 4 bearings, and we have vibration sensors in each one of them, and it is being collected at the edge. Maybe some edge processing is done, sent to the cloud, and we are processing it there. Some of it could be done at the edge. So today, all we do is look at one channel at a time, one channel at a time. So I've called this looking through straws at the world. You just see little bits, you don't see the collection. So to be more clear, today, when you're working on, let's say, channel 1, the only thing that you would do is, stuff at that star marked there, where maybe the amplitude, it could be spectrum, it could be a few things. Or if you're a bit sophisticated in time series analysis, you would look at these green arrows. By that, I'm indicating autoregressive parameters. So lag 1 parameter, lag 2 parameter, etc. But it's still just only about this one channel at a time. So what about all these red arrows? Now, if these 4 bearings are connected to a series of machines, and they are interconnected, and some metal or some work item is going through them, surely the other channels will somehow impact them, either at the current time, that is instantaneous, or in a lagged fashion. So these are all completely ignored in today's IoT signal processing. And all of these causal factors, so they can think of the green arrows as causal factors, and these are also other causal factors. They all together alone can give us the full story. So just a simple example, in the case of, let's say there are 4 bearings, like I said, today we are monitoring only 3 things. And in fact, 12 of these red arrows are ignored. Clearly, it'll have consequences. And the consequence is big, and some of my papers will describe it actually makes the green arrow estimation wrong many times. So not only is that you don't get the red arrow information, if you ignore it, and if that is significant, the green arrow data, those causality would be incorrect also. So a quick example, so let's say you think of an EV and we want to maximize the range of this EV. So we have some battery, some current flow sensor attached, IoT, something monitoring torque at in the motor, and then maybe RPM at this thing. So of course, all those three things are connected, right? So you have to process them multi-channel together, not one at a time. It is then that for each Tesla, so this is not less for the whole fleet of cars or the production, for each one in real time, this IoT monitoring will tell you what is causing what. And remember, cause effect is the critical thing that we may then be able to use performance improvement. Remember, that's what we set out to do. IoT is just doing condition monitoring, saying, what is the current draw or what is RPM? That's great. But what we want is to improve the performance, and that's when this causality comes in. So it turns out this is not just for this application. If you think about it, every IoT application. So what we're talking about here is a really horizontal technology that will apply to a variety of and all IoT applications in my estimation. How are we doing for time? Yeah, I have 10 minutes. So let me give you a specific example. So there's a celebrated, NASA data set. This is actually a 4-bearing setup with a motor driving it, and they recorded the data continuously. So it was run to failure to really produce the information that we can use to analyze things. So just if you monitor the vibration, this is what it'll look like. Day one, nice and small. I mean, this data is there. I didn't show it. But after 7 days or so, the D day, this B1, the bearing 1, died. It had, the rolling elements broken or inner or outer race broken or something. Now, for condition monitoring, pretty simple. Just look at amplitude of vibration. Well, by 16, 17, clearly by 18, we see that it is much higher than pristine day 1. And you can say, hey, shut that down and replace that bearing. Yeah, it's easy. Condition monitoring is simple. In fact, most of the time, so I've done work on this bearing monitoring at Procol Automation. We do more than just vibration. As you know, it's a very brittle measure. So typically you would look at the power spectrum. So you would look at the power spectrum on day 1, this is the power spectrum on D day. You can see big differences. So if you're a bearing expert, you will say, this one, they call it the driving frequency or the line frequency. This is just the motors, that basic frequency. Initially, when everything is nice and clean and pristine, that's the one that shows up. As things get bad, what happens is that driving frequency gets distributed into its harmonic. So you won't see that base driving frequency anymore. And the so-called bearing frequencies start showing up. These are high frequency things that are generated by the many rolling elements and the rubbing against the inner and outer race. That's why those higher frequencies exist, show up. So that's the spread. And so that is what is causing the problem. So here, either by monitoring the vibration or by looking at the spectrum, you can say, there's an impending failure, condition monitoring, all well and good. But the problem is this. So this is the payoff pitch kind of thing. So if this data, if we analyze using this, saying, so there are 4 bearings, so just like the channel picture, you're looking at each of these bearings interrelationship. So these are all causal factors. How much of data that is from the previous sample is causing the current data? How much of the other bearings vibration is causing this B1's, the bearing that fails, vibration, etc. So all these causal factors. So the algorithm determines that. It is fairly complex, but it's been done. And the reason why I'm here is, I'm going to outsource, open source all of the algorithms and details. So the result is just stunning. Again, very easy to see. So because there are so many pieces of information, I came up with what I call fence graph. So here what you have is, this is B1 bearing, B2, B3, B4 in all of them. This is T is the current time instant, that is this point. This is the previous T minus 1, T minus 2, T minus 3, etc. So B1 at the current instant has an effect on B2. That's what this link shows. And the link width is proportional to the causality and so on. But in this picture, all I want you to take away is, in the pristine day, because it's so nice and clean. D day, do you have any doubt that B1 is going to be a problem? All kinds of effects are, and in this case, it could be vibration energy that's going into it. It's sure that it's going to fail. Now, this kind of condition information you could have gotten from vibration, let us say, but I will claim this would be much more sensitive and pick it up. But that's not the value of it, is really how can we improve it? Before I say that, let me just state the main thesis. In IoT, we almost always collect multi-channel data. Why? Because those channels are related. Now, if we don't estimate and work with those relationships, we are throwing the baby out with the bathwater. So in condition monitoring, that may be sufficient. But if you do not take into account interchannel relationships, so these are all technically known, right? That the single channel effects can be erroneous. And of course, ignores this very useful effects between the endpoints. So we need a full picture for it. And this fence causal graph that you saw is what I have come up with. So to look at its real value, as I mentioned, this what if analysis in the technology of causality, we call it counterfactual simulation. So here is the simulation. It's a little difficult to explain, but let me do that. What we want to know is, let me bring this. So, on D-Day, that's when B1 failed, right? What should be the links and link strengths so that B1 on D-Day, we know B1 failed, right? And you saw that picture where everything is flying into it, right? All the energy is going into it. What should have been the links and the link strengths or causal factors and causality on that day so that B1 operates in a pristine way? That is, there is no, there is just that driving frequency spectrum and nothing else. So there is a simulation. It's easy to set up, but so once you have the fence graph, you can use it for simulation, just like some other model reduced simulations and others that are becoming popular in digital twins. But this simulation, of course, is new and based on causality, not on basic physics equations and partial differential equations. This is based on data, what data told us how the causal relationships exist. So it turns out, so when I run that simulation, what I get is, it says, and this is programmatic. So one way to do it is experts will say, that previous one of the links, that was very strong. So if there is a way to reduce that strength, maybe B1 won't fail. But then all these causality interact so much that it'll be very hard for humans to do. So this is done in a programmatic fashion where it said that this would be the link structure that will make B1 operate as if it is on pristine day one. So as you can see, B1 simulated vibration data that has that spectrum, which is like the B on day one, the B1 data on day one. So this is how we would, so at this point, we are not done. We have done root cause analysis. Now these powerful insights have to be made actionable, right? So for that, without domain expert in IoT and IoT, you're not going to do it with domain experts for the foreseeable future, because they're the ones who will say, now this link structure versus the other says, they will know things like, shaft is misaligned, so we have to misalign it. Or when you build the shaft the next time, you have to do some alloy so that it has some strength in certain parts and not in others and so on. So now we've gotten one step closer to actually making the prescriptive analytics, that is We have automated root cause analysis here. And then with the domain expert, we actually then can impact productivity and gross margins for the business. So the big contribution of this is the analytical determination of this configuration through this counterfactual simulation. It's called counterfactual because it did not happen in real life, right? Because the old way of doing experiments is you had to go set this experiment up this way to make sure the B1 data looks pristine. Right? So it's not a fact. We just have the past data. But then because it is causal relationships, we can do this counterfactual analysis. That is what is going to lead to the optimization of connected. This is really, like I said, not for, you could use it for a single asset, a little motor, and monitoring from multiple points in the motor, but it's really for a plant level and of course, smart city level. And like I said, the EV application, that's one of the things I would love to see. So at this point, this is where I am. I'm very excited about this and I want to proliferate this. So the POC need to be done. I write all my code in MATLAB and it's pretty lame code, intentionally so it's easy to debug. These are really complicated algorithms. So need to port it to Python. The fence graph, as I've done, there has to be better visualization. I think of something like a cylinder on which, and the cylinder is rotating, so the causal factors are changing rather than that static fence picture. And we had to work with an expert, domain expert, and say, hey, does these links, does causal factors mean anything? Does it translate? So that part needs to be done. With the NASA thing, I could do it because I knew vibration and I knew bearing dynamics. So, but then to extend it. But ultimately to productize it, that optimization counterfactual I showed, it has to be made industrial strength. So it can be applied unattended in some sense, and more of visualization and so on. So Fred and I talked about it, and my thinking, and not clear whether, to me, it's not clear whether Eclipse is the way in which I can do this proliferation and give away the code and have this made available. So to simplify that, if you go to this website, ScienceSoul, it's just a placeholder of mine. And there is from very gentle introduction to business type of thing, and the hard number theory is the hard theory and the algorithms. Number 5 is probably, if you're really getting into it, the best complete report.